Hello, everyone. And this is the final section of the quarter, 5.3 optimization problems. And there's a few sections within there that you'll be doing. I think 531, 532, and 533. And optimization problems are all about trying to find the max and min. So a few things you'll need to do these problems is just recall that a max occurs when the first derivative is 0. That's a critical point, by the way. We try to use more of the vocab. So max occurs at a critical point and when the derivative changes from positive to negative. And a minimum being the same thing, where minimum occurs at a critical point and when the derivative changes from negative to positive. So max and mins, we're going to be using the derivatives for these optimization problems. And then recall to solve optimization problems, the one hint that I said in the last video or to some of the classes in person is I said the big goal is to get an equation in terms of one variable. Because if you can get in terms of one variable, then we can take the derivative and study its max and min that way. Now, how do we get an equation in terms of one variable? There's actually a trick to this, is how do you do this? Is you need typically at least two equations. So you need at least two equations in which you can use these equations to solve for that variable that you're going to use in that equation for the optimization problem. All right? So this right here, the idea of having at least two equations, this helps with how to get an equation in terms of one variable. Now, some hints to help you with these problems, because it's hard for me to tell you how to do these problems because they're all kind of unique and creative on their own. It's just you approach them with the same idea of what equations can I create? How do I get in terms of one variable? And then I just follow my definitions of max and min. And I'm just careful on my algebra if I'm doing it by hand or with a calculator. So my hint is that for problem 111, the two equations that you're going to use there is you need to use Pythagorean's theorem, which recall that that's a squared plus b squared equals c squared for right triangles, and that determines, the lengths or distances, which comes in handy a lot. This is also where the distance formula derives from. And you'll need to use the idea that distance is equal to rate times time, or more commonly known as d equals rt. So those are the two equations you're going to need in number 111. And you'll combine those two with that problem to write one equation in terms of one variable and take the max and min there. And then my other hint is that when you get to problem 119, is you're going to have to use law of cosines, which recall law of cosines is a squared, should be actually a capital A. A squared is equal to, or then actually use a squared, I'm sorry. Do it with how you're used to seeing it. C squared equals a squared plus b squared minus 2ab sine of c. All right, so for a picture here, we have a, b, and c with angle little c. Would be law of cosines there. And then the other one you're going to need to use is this equation here, which I don't know if you've seen before, the area of an isosceles triangle, which is area equals, so say you have an isosceles triangle that looks like this, where it's A and B, and we'll call this theta, for that angle, is 1/2 A times B times sine of theta. And that is the two formulas you're going to use for 119. Now, if you want to know where this comes from, I'm going to quickly show this. You don't need to know it, but for those who are curious, why that is. So a proof of why the area is equal to 1/2 A times B times sine of theta for an isosceles triangle. Okay. So say we have make a picture here, an isosceles triangle like the following, and I'm just going to call this R, a height h, and a base b, and this entire angle being theta. Okay. Now to get the area of that triangle, and b is just the distance from here to here. So the area of the entire triangle is going to be 1/2 2b times h, for 2b representing the entire base of this triangle. Okay. Now, if we just break apart this in terms of one triangle, so if I pull this triangle out, so that's h. Now that is now half that angle, so that's going to be theta over 2. And then this will be 90 degrees, because obviously the height has to be perpendicular. And this is a radius r. And then the bottom here is base b. Now, since this is a 90-degree triangle, we can actually say that h, sorry, let's not go straight there. Let's do that. The cosine of theta over 2 is going to equal adjacent, which is h, over hypotenuse r. So that's going to equal h over r, which implies that h is equal to r cosine theta over 2. Similarly, we know that from this triangle that the sine of that angle will equal opposite over hypotenuse, which will be b over r, which implies that the base can be written as r sine theta over 2. So if we use these two in our formula up here, what we end up getting is the area equals 1/2 times 2 times the base, the b, which is going to be r sine theta over 2, times h, which is r cosine theta over 2. Now some reordering of things. I'm going to write this as area is equal to 1/2. And the r times r I'm going to bring out, make that r squared. And that 2 I'm going to put in front of these two. So then it's 2 sine theta over 2 cosine theta over 2. So just some reordering and multiplication here. And the reason for that is, recall that 2 sine of, say, theta, cosine of theta, is equivalent to sine of 2 theta. It's a double angle formula. Okay. And notice here we have 2 sine of an angle, cosine of an angle. So this is a double angle, so we can actually write this as area equals 1/2 r squared, and all of that will be sine of 2 times that angle, theta over 2. In which hopefully you see it now, that 2 double the angle of that half is going to net us 1/2 r squared sine of theta. And if you think back to this triangle, r is this side here, and on an isosceles triangle, these are both r. So you can see that 1/2 r squared sine theta would be the same here, which is equivalent to, if I just put a and b right here, that would be equivalent to saying 1/2 a b sine of theta, where theta is the angle in between them. Okay. So there's a little proof, a little bit messy of why that is, but just my hint again is that for 119 you need law of cosines and the area of an isosceles triangle. Okay. And then for 111, Pythagorean's theorem, which tells us lengths and distances, and distance equals rate times time. Okay. So there it is. Do your best on these optimization problems. Be creative. It takes some practice. Is it easy? No. This is a tough topic. It's tough for many, 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 many students. Tough for me when I first learned it, and sometimes even now, if you look at my work when I'm making my answer key, I make a few mistakes along the way that I have to fix. And it's like, oh, yeah. So just stick with it. It gets easier, and you will get a flow of how these work soon enough. All right? If you need anything, come to office hours. Bring that question to class the next day if you have any the following day, and I'll see you then. Bye-bye, everyone.